2.6 Limits involving infinity. Asymptotes of graphs. The outline of this video is as follows. We will begin by exploring the concept of a limit as a variable grows without bound, which we call a finite limit at infinity. This idea is crucial because it directly leads us to defining and finding horizontal asymptotes, which describe the long-term behavior of a function's graph. We will then extend this to oblique, or slanted, asymptotes for certain types of rational functions. After examining behavior at the horizontal extremes, we will turn our attention to what happens when a function's output value grows infinitely large, which we refer to as an infinite limit. This will allow us to precisely identify vertical asymptotes, which are locations of infinite discontinuity. To conclude, we will tie these ideas together by learning how to use dominant terms as a powerful shortcut for determining the end behavior of more complex functions. Let us explore what happens to a function when its input, x, grows infinitely large. This concept, called a limit at infinity, helps us understand the long-term or end behavior of a function's graph. First, we need some new language. When we write that x approaches infinity, we simply mean that x is getting larger and larger in the positive direction without any upper bound. Similarly, when x approaches negative infinity, we mean x is becoming larger in magnitude but in the negative direction. It is crucial to remember that infinity is not a real number. It is a symbol we use to describe this process of unbounded growth. For example, with the function f of x equals 1 over x, as x gets incredibly large, say 1 billion, the value of 1 over x becomes incredibly small and gets closer to 0. So, the limit of 1 over x, as x approaches infinity, is 0, showing a function can approach a finite value as its input grows forever. I will now formalize our intuitive idea of a limit at infinity with its precise mathematical definition, which provides the rigor needed to prove important properties. The first definition states that a function has a limit L as x approaches positive infinity if, for any small positive tolerance we choose, called epsilon, there exists a corresponding number m. For any x value greater than this m, the distance between the function's value and the limit L will be less than epsilon. The definition for a limit at negative infinity is nearly identical, except we must find a number n such that for any x less than n, the function remains within that same epsilon tolerance of L. Imagine a narrow horizontal band around the limit L. These rules guarantee that the function's graph will eventually enter that band and never leave as you move far enough to the right or left. The key takeaway is that the function's values can be forced to stay as close as we want to L, simply by making x large enough. The great news is that all the familiar limit laws we have already learned also apply to limits at infinity. We just need two new foundational facts to get started. First, the limit of any constant k as x approaches positive or negative infinity is simply that constant k. Second, the limit of the fraction 1 over x as x goes to either positive or negative infinity is 0, which makes intuitive sense as the denominator grows without bound. With these facts, our previous rules like the sum and product rule work exactly as before. For example, the limit of 5 plus 1 over x becomes 5 plus 0, which is 5. Likewise, the limit of pi times the square root of 3 over x squared becomes a product involving limits that are 0, so the entire expression evaluates to 0. This means we can now use our existing algebraic toolkit to evaluate a whole new class of limits. Now I will show you a powerful technique for finding the limit of a rational function as x approaches positive or negative infinity. The standard method is to identify the highest power of x in the denominator and then divide every single term in both the numerator and the denominator by that power of x. For example, consider the limit of the fraction with numerator 5x squared plus 8x minus 3 and denominator 3, x squared plus 2. Here, The highest power of x in the denominator is x squared, so we divide every term by x squared. This transforms our expression into the fraction with numerator 5 plus 8 over x minus 3 over x squared, and denominator 3 plus 2 over x squared. As x approaches infinity, all the terms with x in their denominator go to 0. This leaves us with just 5 plus 0 minus 0, all over 3 plus 0, which equals 5/3. So when the degrees are equal, the limit is the ratio of the leading coefficients. Now I will examine the second major case for limits of rational functions, where the degree of the numerator is less than the degree of the denominator. Here we want to find the limit of the fraction with numerator 11x plus 2 and denominator 2x cubed minus 1, as x approaches negative infinity. Following our established method, I will divide every term by the highest power of x in the denominator, which is x cubed. This transforms the numerator into the quantity 11 over x squared plus 2 over x cubed, and the denominator becomes the quantity 2 minus 1 over x cubed. As x becomes an extremely large negative number, all the fractional terms with x in their denominator approach 0. We are left with a numerator of 0 plus 0, and a denominator of 2 minus 0, which simplifies to 0. This illustrates a general rule. Whenever the denominator's degree is greater than the numerator's, the limit, as x approaches positive or negative infinity, is always 0. Let us explore horizontal asymptotes, which describe the long-term behavior of a function's graph. A horizontal asymptote is a fixed horizontal line, which we can call y equals b, that the function gets arbitrarily close to as x heads toward positive or negative infinity. To see this in action, I will examine the function given by the fraction x cubed minus 2 over the quantity the absolute value of x cubed plus 1. The absolute value in the denominator is a crucial detail, as it means we must check the limit in both directions. As x approaches positive infinity, the function simplifies and the limit is 1. However, as x approaches negative infinity, the absolute value term becomes negative x cubed, causing the limit to become negative 1. This reveals that a single function can have two different horizontal asymptotes. The key thing to remember is that a graph can behave differently on its far right side than on its far left. The sandwich theorem is not just for limits at a specific point. It is also incredibly useful for finding limits at infinity, which helps us identify horizontal asymptotes. Let us use it to analyze the function y equals 2 plus the fraction sign of x over x. We know the sign of x term by itself oscillates forever between -1 and 1. But when we divide by x, we can squeeze its behavior. For very large x, the term sine of x over x becomes trapped between two other functions, -1 over x and +1 over x. As x gets infinitely large, both of these outer functions approach 0, so the function in the middle is squeezed down to 0 as well. Therefore, the limit of our original expression is simply 2 plus 0, which is 2. This tells us the line y equals 2 is a horizontal asymptote for the graph of this function. Sometimes we encounter limits that look like one infinite quantity minus another, which we call an indeterminate form. It is tempting to think that infinity minus infinity is simply 0, but that is not always true. We need a method to find the actual limit. For expressions involving square roots, like the limit of the quantity the square root of x squared plus 16 minus x, a great technique is to multiply by the conjugate. The conjugate here is the same expression with a plus sign, the square root of x squared plus 16 plus x. When we multiply the top and bottom by this conjugate, the numerator simplifies to just 16. The denominator, however, still grows towards infinity as x increases. Since we end up with a constant 16 divided by an infinitely large number, the entire expression approaches 0. So, multiplying by the conjugate is a key algebraic trick for resolving this type of indeterminate form. Now let us look at another type of end behavior called an oblique asymptote, which occurs when a function's graph approaches a slanted line as x goes to infinity. This happens specifically in rational functions, where the degree of the numerator is exactly 1 greater than the degree of the denominator. To find the equation for this line, we use polynomial long division to rewrite the function as the sum of a linear part and a remainder. As x becomes very large in either the positive or negative direction, the remainder term, which is a fraction with x in its denominator, approaches 0. For example, dividing x squared minus 3 by the quantity 2x minus 4 gives us a linear part of 1/2 x plus 1, and a remainder of 1 over the quantity 2x minus 4. Because this remainder disappears for large x values, the function's graph gets closer and closer to the line. Therefore, the oblique asymptote is the line y equals 1/2 x plus 1. We can use the symbols for infinity and negative infinity to describe a function whose values grow without bound near a specific point, giving us a precise language for certain non-existent limits. Let us take the classic example. F of x equals 1 over x. As x gets closer to 0 from the right, through positive values, the function's output becomes arbitrarily large and positive. We write this by saying the limit as x approaches 0 from the plus side is infinity. In the same way, as x approaches 0 from the left, through negative values, the output becomes arbitrarily large and negative, which we write as the limit equals negative infinity. The most important point here is that using the infinity symbol does not mean the limit actually exists. This notation is simply a way to describe a specific reason why the limit fails to exist, which is that the function's behavior is unbounded. Now we will formalize the idea of a function approaching infinity at a specific point, which describes the behavior at a vertical asymptote. The definition for a positive infinite limit is like a challenge. You can name any large positive number, which we call b. My task is to find a corresponding small distance, which we call delta, around the input value circa. If for every x within that tiny delta neighborhood of c, the function's value f of x is guaranteed to be greater than your b, then the limit is infinity. For example, if you challenge me with b equal to 1 million, I must find an interval where the graph always stays above the line y equals 1 million. The definition for a negative infinite limit is analogous. For any large negative number, negative b, the function's value must be even lower. This gives us a precise way to describe a function growing without bound. Now let us explore vertical asymptotes, which are vertical lines that show us where a function's output grows infinitely large. A line, which we can call x equals a, is a vertical asymptote if, as your input x gets closer to the value a from either the left or the right, the function's output shoots up to positive infinity or down to negative infinity. For rational functions, a great place to look for one is where the denominator becomes 0, as long as the numerator does not also become 0 there. For example, in the function y equals the quantity x plus 3, all over the quantity x plus 2, as x gets very close to negative 2, the denominator approaches 0, making the fraction's value explode. This confirms the line x equals negative 2 is a vertical asymptote. This function also has a horizontal asymptote at y equals 1, describing its long-term behavior. So the key takeaway is that vertical asymptotes pinpoint the x values where a function has an infinite discontinuity. Now I will walk through a complete example of finding both horizontal and vertical asymptotes for a rational function. First, for the horizontal asymptote, we examine the limit as x goes to positive or negative infinity. Because the degree of the numerator is less than the degree of the denominator, the limit of the function is 0, which means the line y equals 0 is our horizontal asymptote. Next, vertical asymptotes occur where the denominator is 0, which for this function happens at x equals 2 and x equals -2. We can analyze the behavior by looking at one-sided limits. For instance, as x approaches 2 from the right, the function goes to -infinity, confirming that the line x equals 2 is a vertical asymptote. Since the function is symmetric, the line x equals -2 is also a vertical asymptote. By analyzing the limits at infinity and the points where the denominator is 0, we can fully identify all the asymptotes. I want to introduce a powerful idea called dominant terms, which helps us predict a function's behavior by focusing on the part that matters most in a given region. A dominant term is simply the piece of a function that has the largest effect on its value. For our rational function, which is x over 2 plus 1, plus the fraction 1 over the quantity 2x minus 4, the dominant term changes. When the absolute value of x is very large, the fractional part becomes insignificant, so the linear part, x over 2 plus 1, dominates and dictates the function's end behavior. But as x gets very close to 2, the fraction's denominator approaches 0, making that term enormous. Here, the fraction dominates, creating the vertical asymptote. This also works for polynomials. For a function like 3 times x to the power of 4 minus 2x cubed, the highest power term always dominates for large x. Finding the dominant term is a key shortcut to understanding a function's graph. Let us summarize the key tools we have developed for analyzing a function's behavior at its extremes. We have explored two main ideas: limits at infinity and infinite limits. Limits at infinity describe the long-term end behavior of a function as the input x grows infinitely large. If this limit is a finite number, like b, the graph has a horizontal asymptote at the line y equals b. In contrast, an infinite limit describes where a function's output grows without bound as the input approaches a specific number, say a. This behavior creates a vertical asymptote at the line x equals a. For some rational functions, the end behavior is not a horizontal line but a slanted one, which we call an oblique asymptote. By identifying these different asymptotes through limits, we can build a reliable sketch of the function's entire graph. To wrap up, let us review the two main skills for analyzing asymptotes: using formal limit definitions and using degree comparison shortcuts for rational functions. You should now be able to explain that a vertical asymptote at x equals c means the function approaches infinity as x nears c, while a horizontal asymptote at y equals b means the function approaches b as x goes to positive or negative infinity. For rational functions, we found a powerful shortcut by comparing the degree of the numerator to the degree of the denominator. This comparison immediately tells you whether to expect a horizontal asymptote, an oblique or slant asymptote, or neither. For instance, if the numerator's degree is 1 greater than the denominator's, we expect a slant asymptote. Mastering both the formal limit definitions and these degree rules gives you a complete toolkit for understanding the end behavior of functions.